Okay, so as many of you know, if you've been following me, I attended I'm trying to hit the right button here. ReWork AI Summit last week. And so I streamed my sort of first day, and now I'm going to talk about day 2 and all the presentations I saw on day 2. The agenda, if you didn't see it before, for today is to talk about the ReWork AI Summit. HTM Forum Q&A, if I have time. I've got a 10 o'clock stand-up meeting. I'm not sure if there's a research meeting yet. I'm still waiting to hear back from the research team, all of them. Nothing from Subutai or Jeff today, so we'll see what Marcus has, if Marcus has anything. He's not quite in the office yet. So I'm not sure if there'll be a research meeting. And then we will have a building HTM systems session where I'm really happy with how the learning turned out. I know that the last stream ended in failure, but I just needed a little sleep, I think, and everything's all good. And actually, the connection distribution diagram looks great when you add learning, because you can see the connections changing over time, which is, I didn't even think about that, honestly, and it just was very serendipitous. Yeah, I was totally very tired at the end of that day, Mark. Thanks for noticing. So let's talk about day 2. Let's see if I can get this so you guys can see my whole screen here. So the first topic was deep reinforcement learning. This is mostly, I think I did nothing but deep RL on this day. I kept running into quotes. These guys like to quote, they love to relate what they're doing to human intelligence in errant ways. For example, the presenter for this presentation said pretty quickly, it said in his presentation that humans don't do everything from scratch. Now, what he was talking about was prior knowledge. Like when we come into a new situation, we bring prior knowledge to that situation. That was his point. But we do learn and do everything from scratch. I mean, there's genetic predispositions to the way that the neurons in your brain are structured, for sure. My neck is better, Mark, thank you. Yes, 100%, 100%. But all that prior knowledge is something that we learned from scratch. So there was a lot of talk about priors in Deep RL, and a lot of people depend on priors. And that's something that we can't depend on if we're going to build truly generalizable intelligence, right? This was about priors, all about priors in robotics specifically. So they're trying to incorporate priors to find sort of the sweet spot in the policy parameter. Because if you start your hyperparameter search in a bad place in the search space, you'll never get to optimum parameters, because you just search around and it's always sort of flat. You know, you want to look for, there's these sweet spots in the parameter spaces. So he's trying to incorporate human priors, which they're calling residual reinforcement learning, so that they can better choose, I think, where to start searching in that space. I asked the question at the end of this, oh boy, here we go. We do have a fire engine. We always have to stop for the fire engine because it's disruptive and it's fun to watch. Watch out, people. Get out of the way. First thing, 9 a.m., fire engine. Okay. So I asked the question, because there's this theme in day 1, certainly, that we need a realization that RL needed to move towards generalization, find a way to better generalize. So Is this moving away from generalization? He sort of balked at that and didn't really admit that this was moving away from generalization, but said, well, the priors can be applied if the priors are very general, meaning that they're about objects or something. But when I asked him, well, if the priors are general, can they be applied to different robotic situations? And he said, well, that's something we'll have to research. So this, the incorporation of priors definitely seems to be movement away from the area of generalization. So anyway, the technology or whatever he was talking about is called ILQG, which is model-based residual RL, and I wasn't too interested in what it was because it was definitely very specific about one thing. The next presentation was interesting because it was about space and exploration of space and stuff. So there's a company called Offworld. You can, let's see, they have a website that's, honestly, this was, there were some details about this. Let me find the website. Offworld.ai. So great vision. Okay, wow, this is what they're going for. They've got a huge pie in the sky vision about exploring other planets, mining. Specifically, they're focusing on creating robots that can mine on Earth. And so this is something that Jeff has talked about, Jeff Hawkins of Numenta, of a potential really big application for truly intelligent machines. We're talking, you need AGI for this. You definitely need something that can make decisions, can learn all by itself without some round trip back to Earth or back to some servers to do retraining after a new environment is, observed. So a huge vision, certainly, huge vision. Very ambitious, but definitely a big marketing pitch, it felt like to me. I don't know. I mean, they have investors. They're doing research. They're focused on mining on Earth. They have these prototypes of diggers and crushers. Bit King's talking about priors. He quotes. This is back to the previous presentation. I believe that everything you learn is framed in parts in terms of what you've learned before. You learn delta coding based on your prior life experiences. Yeah, so I totally believe this, but this is all about hard-coded priors for each specific situation, and that's the movement away from generalization that I was talking about. It definitely wasn't transfer learning, as from what I could tell. Wouldn't it be more like insect level thinking rather than creative thinking? Oh, you mean as far as the logistics stuff? No, I don't know. I think when you go put these things out in the environment of Mars or whatever, they're going to run into situations that we never anticipated, and they're going to have to adapt and learn or die. So I would say it's more than just insect level thinking. They're going to have to do problem solving. They're going to face situations that an insect would not be able to solve, I think. Yeah, it totally sucks to be stuck with those shackles, the deep learning shackles. That's the world that they certainly operate within. And I'll have some sort of sum up thoughts about this conference at the end, and I'll talk about that a little. So about the mining thing, they actually have these diggers and crushers that they're testing in real mines. Here's sort of an example. Okay, so there's one of the diggers. And this is where they're at right now. They've got a robot arm, and it's got a chisel essentially, and they brought in like an expert mason that they had chisel and showed them like the best way to do the chiseling, and they used what they called imitation learning, and so where they're at is they're trying to maximize the amount of mass that's being extracted with each attack, each chisel attack. So that's what they're working on right now. So they're at the very beginning of this. Now they're trying to do navigation type stuff, but from what I can tell from the rest of the deep learning presentations, they're so far away from being efficient at this. So a lot of these deep learning systems start with humans in the loop. Yeah, you could be right, but you could be right about the insects. I don't know. Ants are pretty smart. Ants are pretty smart. Anyway, so they'll start with a human, and the human will either operate. Hi, Jeremy. The human will either operate the robot, and to give it an example of what it should be doing, sort of like a goal, so it can have sort of a jump start, and I think that's what they did here. They had a professional mason come in and do the chiseling. So the one thing about this is that I thought was interesting is that they do all their testing and training in the real world, which is different from a lot of other systems, because they can train so much faster and more efficiently in simulations. But then those agents, when they transfer from the simulation into the real world, there's a big problem there, because the real world is not a simulation, and there's just so many unexpected things you cannot model, just about physics and about reality that exists in the real world, and the agents fall flat. They can't. Their training does not transfer in most cases, I would say, from simulation to real world. So the interesting about this is they're doing all this training in the real world, and the reward function is all about, for this example, mass mined per attempt. They also talked about using hallucinatory GANs. I didn't quite understand this. I sort of get what they are, but they were trying to do navigation with hallucinatory GANs. But I didn't quite see where they're going with that. So in summary, I think that this company has great vision, and it's cool to think about space exploration and that sort of thing. But it seems really far out, because to be successful at this, you really have to have some pretty intelligent machines, and they're really deep RL seems to be the only game in town for people doing robotics, that or at least the most promising. Hello, Disillusioned. Thanks for joining. I like your Zelda emote. I'm talking about this conference I went to last week, and most of it's deep reinforcement learning. There were some hard questions at the end of this presentation about retraining and resets, and so the presenter, who I think was the founder of Offworld, admitted that there must be retraining on off-world locations. So with the approach they're taking with deep reinforcement learning, they're not online learning systems. So I feel like that's a brick wall. How are they going to adjust in real time to changing situations and environments? I'm not sure. There are certainly cases where machine learning discovers surprising solutions, and we saw that in when I talked Friday about Alpha Star, and about how the tactics that Alpha Star had against humans surprised the humans. They did not expect them to do that. And even in the AlphaGo, again, that really surprised the Go players. The tactics were unexpected and hadn't been seen before, and now Go players are using those tactics. So we humans have learned tactics from these AI systems that we didn't know about before, which is totally cool. Okay, next presentation, and chess. Yeah, absolutely. I don't mean to. I know I'm talking about deep learning, and I am sort of tuned to find the deficits in deep learning because I'm coming from the brain side. I don't mean to come down on it, but because there's so many cool things you can do with this stuff. But I certainly keep seeing the brick wall, over and over again in all these presentations. Okay, so this was towards simplifying supervision and deep meta reinforcement learning algorithms. So they're focusing, they're trying to apply to unstructured environments, and I heard this a couple of times on Friday. Unstructured means basically what we would have like on Mars or on some environment that's not controlled, it changes or it's unknown, which is good to try and focus on those environments because those are the environments that we want to have intelligent things operate in. Today, we don't have anything that can operate in unstructured environments. So we talked about what the problem was. One of the problems is creating a reward function. Deciding where the reward comes from when you have an unstructured environment. If you don't know what environment you're going to be operating on, how do you know what to reward the agent for? What actions to reward the agent for? So coming up with these reward functions is a hard problem and expensive because training. These things have to be trained so much, and that is expensive. It's all compute time. And diversity was a big deal at this conference. So needing to learn a diverse range of skills is important. And the only way that I can see that the creators of these systems add diversity is by hand coding the diversity. So that means lots of supervision and trying to learn faster with less supervision is one of their goals. But it's hard to add action diversity without that supervision. And even in those situations, Mark Brown, you mentioned that they come up with some interesting solutions to problems. It's the diversity, I think, that creates those interesting solutions because humans have to sort of inject ideas into these agents, like tell them do a lot of this and then do a lot of that or something. And then once they have agents that have certain strategies and then they play them all against each other, that's one of the things deep learning can do. It doesn't need a ton of data. Not deep learning, deep reinforcement learning. You don't need a buttload of data like you do for deep learning networks, like millions and millions of images. You can create these agents and then play them against each other. So they sort of create the data themselves, but you do have to inject strategies, or that's what they're calling diversity, different strategies, different ways of being rewarded for different actions, for each agents. And then as these agents that have different strategies play each other out, and you find agents that this emergent behavior sort of comes out of that diversity, which is like combinations of strategies that haven't been tried before, right? Yeah, diversity is huge, and everybody, and it's such an interesting topic because diversity is important in life just as well, as we all sort of know, I think. Mark said it's such a different way to work as it only stimulates a single aspect of the brain. It applies simple point neurons, but the thing being emulated is the layers to parse, dissect problems, space, and manifold topology. Yeah, it's very hard to visualize these things, I note that HDM has backed away from this aspect, so it may be too soon to poke fun at DL. I'm not trying to poke fun at DL for sure. I think deep learning is very cool. But I'm more interested in brains. And you're right, there's population effects. Hey, thanks for the follow, CM Griffin. I watch your channel quite a bit. He's raiding. Thanks for the raid. Appreciate it. I'm talking about deep reinforcement learning, because I went to a conference about deep reinforcement learning on Thursday and Friday, and I'm going over some of these presentations that I saw there. Awesome. So we're talking about diversity right now in deep reinforcement learning because it's very important to have diverse actions. There's a cop going after somebody. See that motorcycle? That's a cop. So meta RL is leveraging prior experience to try and quickly learn new tasks. So I think it's sort of a way of transferring the learning that you've had in other environments to learn new tasks. But it still requires supervision. And all of these tasks, even in meta reinforcement learning, still need reward functions. Here's just a peek into some of the math. I did not take pictures of the math at this conference because I'm not a mathematician. I'm not really great at math. But a ton of these things, these presentations were focused on robotics. Towards supervised meta-reinforcement learning, there's still going to be a human in the loop in this example. You need a human trainer. And they even talked about language in the loop reinforcement learning. And there was a couple presentations that talked about this. And this is about like having basic language understanding so you can give high-level commands. Thank you, Fruit Shop, for the follow. Appreciate it. And things like move to the left a bit or move up a lot or stuff like that. If you can have basic commands like that, and this is sort of the human in the loop, it gives you the ability to have less intervention because you're not necessarily retraining. You can adjust the agent's behavior by giving it a few small commands, and then it will get its rewards and sort of learn from those adjustments. But you still have to have a human labeler, like move closer to the green triangle. So we can understand commands like that. And then the agent can respond, and once he gets a reward when he gets to the green triangle, it gets a reward for sort of higher level commands, which is the tasks that the agent is trying to accomplish. Mark says if we did do the hierarchy with HTM, it would not do reward functions. This will be breading some serious new ground and huge new potholes to step in. Yeah, I agree. I think the hierarchy in the cortex is not. When they talk about hierarchy, and there's another presentation I think that talks about hierarchy and deep reinforcement learning. And I don't think it's the same thing as the hierarchy we talk about in HTM. Okay, so this supervised meta RL, when you have a human in the loop, it works better than just straight rewards, but it takes more effort. Unsupervised task reward extraction from the environment. I think you just mentioned that. I'm not sure that that's a thing. Oh, here it is. How? All right, so they start with like random reward functions when they're talking about unsupervised meta learning. Let's see if we can parse this slide here. So for unsupervised meta learning, let's see, you have your environment. Here's the meta RL loop. So the meta learned environment specific algorithm uses some reward function, has some fast adaptation, but I think less overfitting to task distributions. Random reward functions, they start off with random reward functions and they sort of evolve over time. And again, they are diversity driven. I don't know how that works when you're diversity driven using random reward functions. I guess you can reward. I don't know how you identify diversity in random reward functions, but maybe you can. But you still have to, maybe that's how you do diversity. You start with a predefined set of tasks. So those tasks could be the diversity, where you're using diversity. So closing the task proposal loop. Yeah, it's all about priors. A lot of this stuff requires priors. They can't get anywhere without the priors. So the takeaway from this presentation was that supervision is extremely important for solving deep reinforcement learning problems. And this is sort of a common theme. A lot of the takeaways from these presentations were like, we need priors, we need supervision, we can't generalize, which is unfortunate. Okay, I'm gonna move on to the next one. This was a Facebook AI talk, AI research about lifelong learning and robotics. So same goal as a lot of the others. Disillusioned has some priors. So everybody wants to have autonomous robots, right? And everybody's looking at deep reinforcement learning for the answers. And they're assuming that this is the way to get autonomous robots, because for most of these companies, it's the only game in town. It's the most impressive form of deep learning that we have at the moment. They're all referring back to these big milestones like AlphaStar, AlphaGo, all the games that they can play and beat and everything. And again, this woman made a reference to how children learn. I'm always very wary about that. But anyway, humans remember their errors. So here's the whole point of this presentation is that humans remember their errors and use them to learn faster. So how can we get deep RL systems to do the same thing? So she's barking up the right tree here, right? Learning how to learn is super important for autonomous agents. And she's trying to teach these robots how to move and the effects of their actions by separating out the errors that they've made and transferring those learning rates. I don't know the total details behind this, but somehow if you can take, as an agent operates, you can take its learning rates over time, which incorporates the errors that have occurred, and somehow apply those learning rates to another environment that it goes into. So you can separate that model with that memory of errors, like it says right here, or learning rates. And then when you go to a new task, you take that memory of all your errors with you. And apparently that's easier to transfer when you're talking about learning transfer. So their experiments were trying to do that sort of thing, but they're super simple experiments, like a robot. So this is the task that they're talking about. A robot picking up nothing, that's one task. A robot, I don't know how you give a reward for that, but a robot picking up a light object and a robot picking up a heavy object. So this is like a super simple model, one model per joint in the robot arm or whatever. And basically transfer learning that includes learning rates, which includes the errors, the learning rates or the errors, and try and transfer that to the other tasks. So they successfully took errors from a robot picking up no object and applied it to picking up a light object, picking up a heavy object, and essentially it learned faster than starting from scratch. So that's what they did. One takeaway, and I heard this over and over again, is online learning is really hard. That's a direct quote. Okay, so here's some more mathy stuff if you want to look at it. So here's the law about learning the loss function. So you have to have this differentiable framework, high dimensional. And she says both meta loss and learning rate are learned. I don't totally understand what meta loss is. A lot of talk about meta stuff. Let's see. Here's one thing. You still have to provide a task loss function. This is human coded. You have to create this yourself. You can change the policy with more layers or other architectures. Yeah, but they are just starting on this. This woman was very excited about this, but it was a very simple experiment. You're just talking about robots just lifting one thing up and down. That's it. So that's state of the art. Okay, next one, continually evolving machines learning by experimenting. There's a lot of research scientists from Berkeley presenting here. So the idea was, again, to equip reinforcement learning agents with prior knowledge. A theme at this conference certainly was starting with prior knowledge. He did ask some interesting questions. Like, this is the first person to refer to object representation in any way that I could tell. So he asked the question, what is an object? What do you have to understand what an object is? And then, from what I could tell, didn't really answer it, you know. And again, there's this reference to infant learning, saying that play is a form of experimentation. Absolutely, spot on, you know, and our brains were pre-wired, we're wired to enjoy learning and exploration. That's the thing that we have to add to these agents if we want them to be smart and to learn. We also imitate other agents, which is true. A lot of talk about imitation. So this is at its core trying to address the problem of object representation. The object is a collection of perceived features. I agree with Mark there, but that's not what anyone at this conference was referring to objects. They were referring to, there's really no, as far as I can tell, I don't know, they don't think about it in the same way. Absolutely. So trying to, let's see, the inverse model of action prediction instead of pixel prediction. Oh, right. So usually in these robotics deep RL systems, there's a camera and a robot, right? And the camera, the pixels in the camera are what is fed into the deep reinforcement learning system. Just like when they do the Atari games, they feed every pixel into the system. Every one of those pixels is a part of the state. So it's the same thing with the camera. Every pixel in that camera frame over time is part of the state, and that's what the system learns on. And the interesting thing about this is that they're doing this sort of inverse model of using the action prediction as the state instead of the pixel prediction, which I thought was interesting. Also said random exploration is limiting because the actions should increase exploration. So that's a good point. If you just start with random actions, you don't explore the whole space. You know, you end up just sort of what you want is semi-random actions, pseudo-random actions that can optimize on exploring new space, right? That seems to be the right way of doing it. So they came to the same conclusion, which is good. Driven by curiosity, which is that's a good concept. So this is interesting. So they are actually training agents to maximize prediction error because that tells them that they're in a space that they don't understand. So that's an interesting way to think about it. And they call this in a way it's like self-supervision because you're incentivized to go places that you don't know and experience things that you have no model of, right? Novelty seeking, yes, exactly. But there's too much to learn, so you need to use imitation. So they, again, going back to priors. Imitation is about prior knowledge. At least in the deep RL world, it's about priors. So it's interesting that you can treat prediction error as a reward function to train the policy. That's kind of a cool idea. So that's what I took away from that one. So here's another Facebook AI research called Habitat, a platform for embodied AI research. I was a little bit harsh on this. He didn't have a completely wrong definition of embodied AI. But from his perspective, his embodiment means in a 3D world. Okay, I don't quite agree with that. I think you can be embodied as long as you can take actions in an environment and perceive the changes to the environment based on those actions. I think that's embodiment. I don't think it's not about a 3D world, any dimensional world. It's just about a world and a self and motion or movement in that world and the perception of the changes to that world. You know, that's more how I think about embodiment. So the habitat thing he was talking about was a project that he's been working on. One of the things I wanted to look at was this Matterport 3D. If you're interested in 3D environments for exploration for agents, this is really interesting because they have this technology now where, you know, people will come into your house, for example, and they'll set up things all around the house and take all these pictures so that you can basically fly through your house and get this super high resolution, you know, graphical interface of your house. Like this is one of the pictures of someone's kitchen, and you can go all through it, and all of these objects are tagged, you know, and you can interact with them. Well, not eventually. I mean, his system creates something sort of on top of that can interact with them. So they're trying to create like an image net for embodied AI, and they're calling this Habitat. It's a 3D simulator. And I was confused because he kept talking about how like the resolution is so high. So like Unity, when you're playing a video game, when a human's playing a video game, the refresh rate that we pay attention to. Thank you for the follow, FP Jesta. When humans play video games, the refresh rate that we notice, I think, is like 25 hertz or something. Like anything, or no, it's 60. Sorry, 60. It's right there on the slide. It's 60 hertz. anything over 60 hertz we're not going to even notice, right? Humans do not process input that fast. So like Unity, I think runs at like 25 hertz or something, and it looks fine to pretty much everybody. But it's at a higher resolution. So what the machine would rather have is a smaller resolution, but at a faster refresh rate. So I was totally confused by this, because I'm like, if we're talking about hertz as far as refresh rate, why that just seems like a ton of duplicate information. But he's not talking about actual perceived refresh rates. He's talking about how quickly this system. Thank you for the follow. I don't even care 12. I appreciate it. Talking about deep reinforcement learning, a conference I went to last week. They're talking about how quickly this system can update so that a deep RL system can learn fast. So it's not about how quickly or the amount of information coming in per second for it. It's like how fast can the agent, train, essentially. How fast can it train? So it's not really a refresh rate, but a rate at which the agent can take action. So this is really important because all these agents, or lots of these agents, they're all training on these big cloud computing systems, Google Cloud or AWS or whatever. So they're operating way faster than the speed of reality or whatever that we operate at. Like I said, if you watch my video from Thursday night, Alpha Star, which is the deep reinforcement learning system that it was actually LSTM with a bunch of other things, but Alpha Star, which is the system that beat the Grandmasters of StarCraft 2 10 out of 10 times. That agent, the agent that they ended up with that beat those Grandmasters, trained for over 600,000 years, which I'm still so blown away by. That's amazing that there's that much compute. Imagine the carbon footprint of that. It's just amazing. Okay. Next up, this was a dense conference, man. Another Facebook AI researcher. So this was all about the sense of touch, which I thought was cool. It's really the only person at all talking about the sense of touch. So he's emphasizing forces when you interact with the world, and this is something that most of the other people doing robotics are not even paying attention to. I mean, there's torque, and usually they're just hard-coded things like don't squeeze something too hard. But he's actually got a really interesting sensor that they've created. Most of the stuff we already know, humans create models of the world, but robots don't. He's trying to use tactile sensors, right? So the one thing is called gel sight, which is this interesting sensor, but this was basically a presentation about this gel sight sensor. It's hard to see it, but this is it right here. There's two of them on either side of this little thing, and this is sort of what it sees. So this is an interesting little technology because so imagine that this is like the gel sight sensor, and you put a camera inside of it, and it points up, right? I could probably draw this better. So on top of that cup, you put this gel, right? And then you put a grid on it, like you actually draw a grid on it. And then and it's very plastic, it's very flexible. So then when it touches something, as you can sort of see here where it says gel sight left and right, these are the impressions left on that gel by where it's touching like this picture. So you can see a pointed, like this is the right one where it's hitting the point, and you can see it's a lot of pressure, and this one is sort of more rounded where it's touching the handle. So this is super cool, I thought, because you get a lot more, you get the tactile information out of it. So he was working on creating robots that could better understand and incorporate these types of tactile responses, and it helped with grasping, Like one of those visualizations where he'd show a picture of two robots that essentially were grasping the same thing, and you'd say which one's going to fail and which one's not, because you can't tell, and neither can the robot from the picture, whether it's exerting enough pressure on the thing for it to actually hold. But with something like this, you can tell exactly how much pressure is being exerted. So that was interesting presentation. thought. This one got canceled. Okay. Autonomous driving decision making with deep reinforcement learning. So this was about urban driving, and this was really, this really is a window into where we're at right now as far as autonomous driving. Because so he's working specifically on situations that you come across in urban driving. Pretty much all of the autonomous driving vehicles we have right now are highway only. They can't make too many decisions. It's basically, navigate in a highway setting. Don't drive it on the off roads. Don't drive it through the city. You can't do that sort of thing. So they're trying to tackle these really challenging environment. Urban driving is hugely dense when it comes to sensory information and all the decisions that need to be made. So we're talking about very high dimensional data. Everybody in this space, this is what he said, is using a hard-coded modular approach. So the current approaches in the industry, he's saying, is very modular, but all of these boxes are hard-coded. There's no generality. And so that's sort of the challenges at the bottom here: accuracy, generality, and system complexity. So in order to adapt to these constantly changing environments, you have to constantly optimize the deep RL policy. And again, he talks about imitation learning, which is priors, essentially. But even with imitation learning, you can't learn skills if there's no representations in the training of those situations, right? Most vision systems and motion systems are currently hard-coded too. So deep reinforcement learning just needs a simulator, so they're doing all this in a simulator. But for urban environments, deep RL is still not very successful. And the reasons he's pointing to, what some of them are, is that they're still using outdated reinforcement learning algorithms. You got to remember, deep RL is only like 5 years old. That's super new, in this world. And he says that there's new algorithms being published in arXiv like every month. So it's very hard to keep up to date. This research is super expensive. All the training that's required is super expensive too. Let me think. I'm trying to figure out. So their experiments here use this LiDAR, and this is sort of an example of the image that the LiDAR gets. They actually put the LiDAR way up on top of the car, so it can look down and get a better perspective of it, and it tries to differentiate, things that are at up high versus down low. And try and pull out, dimensionality, essentially, reduce the dimensionality so that the RL agent doesn't have as much to process. So they're using a variational autoencoder reconstruction pipeline, but there's still nothing similar to object understanding in this. It's still, probability distributions, etc. So this is sort of what they're trying to get to. They have a map. They've got objects that they've detected where, like an egocentric state, and then a route, and then this is basically what they're working with, this bird view image. That's what they're trying to reconstruct and make decisions off of. And this is sort of what the LiDAR looks like. So the input up here at the top, and then they reconstruct it. I don't know exactly what the difference between these is, but essentially they get to this mask down here. So they take this and they process so that they can reduce the dimensionality so the reinforcement agent doesn't have to deal with all of those bits. So they're not just feeding the LiDAR data straight into the DRL. That would be way too much. So they're doing this pre-processing. There's one of the presentations did talk about SLAM. I don't remember which one, but it was as a comparison, I think. So they've got all these model-free algorithms they're trying, and they showed all of these, and I did take pictures because it was just math. DDQN, which is a common one, DT3, and soft actor critic model. These are like some of the common deep reinforcement algorithms that are around right now. So Carla is the simulator that they use. That's the name of the car simulator, Carla, which is fun. He said they did it in a simulator because you wouldn't want to run a real RL car in the real world. Which emphasizes none of the self-driving cars currently are using reinforcement learning. This is not a technology that's currently deployed. There's only one place in this whole conference that I could tell something was actually deployed in reinforcement learning in the real world, which I'll get to. So what they tried to do was the roundabout. And I think I have a picture of this. So the goal was to navigate a roundabout. That's what this whole presentation's experiment boiled down to. How to navigate a roundabout. And it was basically enter the roundabout, ignore the first exit, ignore the second exit, exit on the third exit, don't hit anything. So they were rewarded for progress, getting to the first exit, getting to the second exit, and then finally getting passed out of the roundabout. So they would penalize for collisions, they would reward for progress through the roundabout, and they tried this with and without the surrounding vehicles. They found that the soft actor model worked best, but this is a very restricted experiment. It was just one example of a roundabout, and they just went like sort of 3/4 around the loop, and there's no noise at all in the simulation. So with deep reinforcement learning, they were able to navigate a roundabout. That's what this was about. Okay, another robot one. I think this was the one that actually has something deployed for reinforcement learning. If you want to look into it, the company's called Osaro. So they're really working to do reinforcement learning for robotics tasks, and they're a company trying to make products. Most robots, they say, have only a level 1 autonomy, which means single automated operation. And there's a ton of robots that have single level 1 autonomy. And you can go look up the different levels of autonomy. I think there's 5 of them. 5 being fully autonomous, level 1 being just one single automated operation. So I think they're getting to like level 2. They're trying to get to level 2. So what they're trying to do is essentially target the warehouse space because it's not an unstructured environment. You know, a warehouse is a structured environment. They know there's going to be a bin here and a bin there, and there's going to be stuff over here that needs to be put over there. So it's basically pick and place in warehouses. That's what they're trying to automate. Skynet is level 5, yeah. So not just pick and place, but also put it in the right place. Let's see. So these are some of the robots. Some of them are suctions. Most of them are suction. It's easiest to pick up things with a suction cup than it is to grasp it, because all you have to do is put it in the right spot. You know, you don't have to worry about. So all these that I saw in her example were suction cup sort of collection. So they have to collect real world data. This is something you can't just do in simulations. You do testing in simulations, but in the end, you have to test also in the real world. All of their data and their models are in the cloud. They're in structured warehouse environments. Only deep learning solutions currently deployed. Here's the one. So there's this, here's the one robot they've got up here on the top right. And there's a video of this if you're interested in looking at it, but it's not very exciting. But essentially, there's a plate, right? And the plate has 4 bolts coming out of it. So the task is for the robot to put another plate on top of it with 4 holes. The problem is the plate might be a little oriented differently. So the deep reinforcement algorithm puts it on there, matches automatically the holes no matter what orientation the plate is in, and puts it on. That's the one example of deep reinforcement learning in the wild that I saw from this conference. But at least there's something, because I didn't think there were any robotics applications that were using deep reinforcement learning out in the wild, and there are. So should run watch a delta with grippers running at blurred speeds driven by a vision system. I'll have to check that out. Excuse me. Okay, I need to go fast because we will have a research meeting in about 20 minutes, 30 minutes maybe. And I have to be at my stand-up soon, so I'm almost done here. Can deep reinforcement learning improve inventory management? This was a logistics application, which was interesting, not a robotics application, and it seemed to be somewhat successful. And this is basically supply and demand. I've got all of these centers that supply product and all of these centers that need product. and keeping track of the best way to route the product to these centers at the right times is a big problem. Do you go fast and expensive, which is like shipping over with a truck, or do you go slow and cheap, which is like a train, which gives you more? So there's big logistics problems, and this person who was in more of the operations space was applying deep reinforcement learning to try and decide when to replenish stock to the different systems and what orders to make. And he seemed to be having some success with that. So I thought that was cool. Okay, I was interested in this because the word reason was in the title. Learning to reason, summarize, and discover with DeepRL. This is from Salesforce. Let's see. He went through these 3 different case studies. I lost interest in this when I realized that reasoning was a knowledge graph. So really, when he said the way he wanted to the way they defined reasoning was having a pre-existing knowledge graph, which is a prior information. Could be a very deep knowledge graph, and reasoning is basically navigating from one node to another. So asking the question, what directors has Tom Cruise worked with, for example? So the reasoning would be, okay, let's go to Tom Cruise and let's look at all the movies. So the first step is finding all of the movies or all of the projects that he's worked with, and then the next step of saying for all those projects, who is the director, and then making a list of those things. So that was the type of reasoning that they're talking about, which is navigating a knowledge graph. Sometimes these knowledge graphs have missing links, and what this DeepRL system does can guess the relationships without those missing links. But it does need to be sort of hard-coded with this path diversity, which is part of the knowledge graph. Okay, that's it. Okay, so a couple of final thoughts, and then I'm going to take a break, and I'm going to prep for my stand-up meeting, and then we're going to have a research meeting. So let's do this. So this is worth going to because just for my own education, I know a lot more about deep reinforcement learning today, even though I have never created a deep reinforcement learning system. I think I understand the nomenclature a bit better, and so it was good education for me. I was wondering what the state of the art was currently in deep reinforcement learning, and so it was a good sort of indication of what the state of the art is. No one seems to have any illusions about what you can and can't do with deep reinforcement learning. When you talk about AGI at this conference, everybody thought AGI was a long way away. Thinking about DeepRL. And from the standpoint of DeepRL, AGI is a long way away, which I would say, I agree. There's a ton of challenges. The major challenges are generalization and training speed, scalability, right? That's the things that everybody acknowledges are the major challenges for DeepRL. And no one really understands how to attack those problems. They know that we need benchmarks, and so they're working on benchmarks. And there's and people are working on lots of different ways to attack those problems. And a lot of the tactics that are being applied today involve prior knowledge. So, which goes against the idea of generalization. So, one of the ways you can try and decrease training time and increase scalability is by injecting prior knowledge, which is completely the opposite of what you want to do to achieve generalization. So there's this dichotomy here, and everyone agrees that this is a hard problem. There's a lot of hard problems that need to be addressed in the deep reinforcement learning world. And everyone, I think, understands that that's the case. So I don't think there's many illusions about it, and there's a lot of, I hate to say nostalgia, because this is just all these breakthroughs just happened, but there's a lot of looking back at the big breakthroughs from AlphaGo, from AlphaStar, from all of the different gaming environments that DeepRL systems have conquered recently. Montezuma's Revenge, there's a lot of references to that. Like, if we can do that, we can do anything, right? Sort of thing. But the problem is that just doesn't transfer. It's very, very hard to take those very hard-coded solutions in those specific environments and transfer any of that learning into environments that are even a little bit different. That's a big challenge. So that's the recap of the conference. It was totally interesting. If you're, I liked the conference organization. ReWork seemed to do a good job putting the conference on, so I gave them kudos as I was going out the door. Told them thanks for the great conference. So that's where we're at. And so I'm open for questions or comments now. I am going to go back to my title.